Oh,
Okay, so thank you very much, Ehsan, and thank you very much again to everyone for joining today. And today we have our speaker, well-known speaker, Ehsan Lee, and he will talk about the concept of continuity in mathematics and why it's so important and so powerful. So please, Ehsan.
thank you, Ajit Bhai, for the introduction. Yes, today we will be discussing a bit about continuity and why it has been so important. And many of you who have done math courses already know that continuity comes up in many courses in undergrad, graduate, and it is a very fundamental concept in maths. So today I will try to answer a few questions about it. Particularly, we will understand mainly why continuity is so important, why it is so popular, and also we will see some definitions, that one definition that you saw in calculus and two or different definitions you saw in real analysis, and I will try to explain why all they mean the same thing. So let's begin in a very simple manner. First, we try to understand that in any subject of mathematics, you must have studied functions. I mean, that was maybe the first thing you studied. In algebra, you study homomorphisms, yeah, isomorphisms, in vector space theory, metric space theory. Different theories have their own functions. Topology has homeomorphisms. So in general, we study functions between two sets, and we hope to relate the sets and the structure on those sets using those functions. But just a function is not important. Sometimes we need more powerful notions. Continuity is one of those notions where two different sets with structures can be linked together. In the sense of analysis, it can be in the sense of topology. There are many ways to look at continuous functions. Today we will be focusing on calculus and linear analysis, and hope to find a way to look at them in an equal footing. We'll try to see them as the same thing. So uh, yeah, and as I remarked before, that definitions in calculus and reanalysis are very different. How you use them, how you apply them in both courses is very different, and we will try to see a few examples as well. Okay, from calculus. This is a very well-known definition. You can find it in any calculus book, that a function f r to r is continuous at a point a real number a, if this following equation holds: that the limit as x approaches to a of f of x is equals to f of a. Now, this seems like a very innocent definition, but if you recall your calculus theory, you first understood what a limit meant. You understood what functions are, what a set is, a function between sets. You did a lot of theory before you even wrote down this thing, and that was necessary. So, although it might not seem that this is a very involved definition, it is very, very involved. And just to show you just what this little line means, there are two main important things that you need to understand. One, we know that the limit as x approaches to a f of x, it exists. And what does that mean? That means that the left hand limit and the right hand limit are equal. You might recall many applications that you did on computing left hand limits. You may have used computation method where you randomly put in values close to a for some given function x, and then you try to evaluate if it's continuous or not. Oh, and the second thing it implies is that the left and right hand limits are equal to f of a. F is defined on a, so f of a is some another real number. And this definition, if it is a local definition, and continuity in every theory is mostly defined as a local property. When I say local, I mean that it is defined at a point. It is not defined on a set directly, but we go to define it on a set, that we say the function f is continuous. Sometimes it says f is continuous on r, the real line, if it is continuous at every point on the real line. Okay, so this is a simple way how any calculus course would have started to define continuity, and then you saw some examples of continuity, continuous functions. A geometric way of thinking of continuous functions. When you are given a continuous function, the first thing that comes into your mind might be a curve like this that you can see on with the blue curve over here. And your instructor, your lecturer would have tried to convey to you why x approaching to a on the x-axis over here implied that fx approaches to f of a on the y-axis over here. And it approaches from both sides, the right and the left. That is why when those left and right limits equal and they equal to the value of the function at that point, that is when you have true continuity. Okay. And to give an example of a function that is not continuous, this is a very simple, a very weird example where you can see that there are points where the function is not even defined. For example, on x equals to 1, the function is not defined. On x equal to 3, the function has a jump discontinuity. This is formally called that. And on x equals to 5, this is also a form of jump continuity where the left and right hand limits are equal, but the function value is not equal. So at each point, you can see some condition breaking for that definition. Okay. And in calculus, when you began, there were some basic properties that you were told that if two functions are continuous, then the algebraic operations you have, for example, the sum of two functions. When I say you add two function, I mean that you add f of x and g of x. They add pointwise. Similarly, c times f, which is a scalar multiple of the function f, or the product function f g and the quotient function f over g, they are all continuous, but for the quotient we need to be careful that gx should not be 0 for any x belonging to R. Otherwise, the quotient function f over g will not be defined. So this must be a basic property that a basic theorem that you would have studied right after you studied the definition. And I will also tell you why. I'm just going to tell you why, but in a moment. First, let me just tell you a few results. Then another theorem was that if two functions are continuous and the range of f, meaning the set where f maps everything to, if that is contained in the domain of G, then we can define a function which is the composite function G compose f. And clearly, if the image of f is not defined, is not contained in the domain, then this function first it evaluates at f of x. And what if f of x is not defined, or G is not defined in f of x? So we would run into definition problems. So for it to be well defined, we need this condition on the range and domains. And this function defined like this is also continuous. Now we have these two theorems. We always went through these two theorems. The question was, can we say that the reverse as x approaches to a, f x approaches to okay, well, first thing, Amara, that you wrote that x approaching to a implies fx approaching to f of a. That is the true definition of continuity. But I understand what you're trying to say. You mean that f of x approaches to f of a implies x approaches to a. That is not exact. You won't call that continuity. That is a different form, different thing. To see what that actually means, I will answer this even better when we get to the real analysis part, because then we will see implications. For now, because we're in the calculus world, I will put a pin on the question and I will try to answer it when we have more rigorous tools over here. Okay. So as I said, in calculus, if you remember, you were never even told what epsilon or deltas are. And I'm pretty sure if you were given a function, for example, if you had, sorry, for example, if you were given the exponential function, meaning the function f of x equals to e to the power x, if you remember carefully, did you even ever check that the limit definition? Did you ever check if this definition at any point, did you evaluate the limit? I'm pretty sure you did not. Okay. Similarly, for example, f of x equals to x squared, which is a polynomial. You never check this definition if this hold. If ever this holds for every point. Why? Because these two theorems allowed us to generalize and give us examples of different functions, different continuous functions. For example, if I just told you and if you just believe me, if I'm not going to tell you anything else, these two functions, if you believe me, are continuous, then we can build many continuous functions just by knowing these two. One of them is the constant function, and f of x equals to c, where c is any fixed real number. Okay, this is called the constant function. It is a continuous function. Okay, I will show you the graph as well for you to believe me a bit more. But if you just take my word for it, we can build many more things just from this. And the other function, f of x equals to x, which is the identity map, or in other words, the y equals to x, which is just a line. If you see the graph of it, it is just a line in R2 in the real plane. So these two functions are continuous. And just to make you believe me, I have first the graph of the constant function. You can see that in the rough sense of continuity, it is continuous. It is not broken at any point. There is no jump discontinuities. There is no removal discontinuity. There's nothing. It is simply a straight continuous function. Similarly, just a different, you can say that this is a rotated version, but okay, it's not right to think that way. Just think of this as the line y equals to x, which is the diagonal in the real R2, the real plane. And these two functions, I hope it isn't this much intuition is enough for you to believe that these two functions are continuous. Now let's build some continuous functions. First, just by knowing these two, I want you to think, can you prove somehow using the theorems before that polynomials, this expression, which is a finite sum of a linear combination of monomials, is continuous? I think we can go there. Why? Because, for example, we can prove this by induction. First, base case, if for n is equals to 0, we would just have this last term, which is c0. And p of x equal to c0 is a constant function. So there's nothing to check there. It is continuous, right? Similarly, we will go for another base case, which is n equals to 1. And then we would have maybe just c1 x1 plus c0, which is just a translation of a, which is you can think of as the sum of two continuous functions. Actually, first you can see it as c1 into x is a continuous function by the theorem, because any scalar multiple of a continuous function is continuous, and then the sum of two continuous function is continuous. And then in the inductive step, it is very easy to see, say, if this part is continuous, then again multiplying is continuous, scalar multiplication is continuous, and then adding is continuous. So this polynomial can in the end be proven with induction. You can prove easily that polynomial is a continuous function. And I did not even use the limit definition or any limits over here. Okay, just by using those two theorems, which were very fundamental. The next thing is rational function. Rational functions are continuous where they are defined. As you can see, the theorem states that these are continuous where they are defined. For example, the rational function px over qx will not be defined when q of x, the denominator polynomial, is equals to 0. In other words, the roots of the polynomial in the denominator are those points where this function, this whole quotient of two polynomials is not defined. And by the same reasoning, the same theorem, since we know polynomials are continuous, and the quotient of polynomials of continuous functions is continuous if the denominator function is never equal to 0. That problem is also avoided when we said that where they are defined. So we can maybe build slowly and slowly to see that this rational function is also continuous. Trigonometric functions. Now this is a bit more difficult to see directly, but I claim to you that we just need one more small tool, which is, if you recall, the Taylor approximation of these transcendental functions, the sine function and cosine function, we can write them as series, and series of of simple monomials. Like, for example, the if you remember the sine of x series, if it is just all the sum of the even powers of x beginning from x squared, yeah, beginning from x squared and then going on till x4, then x5, and some with some constant attached to it. So you can believe that it is also a sum of monomials, right? Not a finite sum, it is an infinite sum, and we need some more results, but I don't want to get into technicalities. So, but you can see why these all of these have series, and hence they are continuous. And finally, the infamous exponential function, and sorry, and the logarithmic function. These two functions we know by their nature, by their definitions, by their graphs, they are continuous functions, but we can use this series result as well to convince ourselves that these are also continuous functions. So did you see why I did not go into the definition? I did not do anything. I just used these two theorems, or actually the first theorem, again and again. So, and in mathematics, we can do this easily if we have some result, that if we have one result that generalizes many things, and we go through the effort to just prove that one, our job will be very simple to make new results. Okay. So that was the end of the calculus section, and I'm pretty sure you all then, when you were in the calculus course, you then started to started working on differentiation, and then the continuity discussion was ended over here, just so you have a class and of a very big class of continuous functions, and just these five. If you just imagine, there are infinitely many possibilities for these: the scalar multiples, add additions, the quotients, the products. You can make so many functions just by knowing these five categories. So this is where you went beyond continuity in calculus. But did you notice that there was no hardcore theory? There was no epsilons, no deltas that are in that come up in analysis. So let's just review a little of real analysis. And in real analysis, if you remember, there are two infamous definitions of continuity. The first one, any math student, undergrad or grad, who has been through analysis knows by heart. And I'm pretty sure there are some memories coming back when you read this, that if f is continuous at a point A, if for every epsilon greater than 0, there exists a delta such that this implication holds. Now, Amar, to your question, when we see, before I move further, when we see this implication, right? This implication, if you reverse this, but observe that this definition does not only include this implication, it includes the epsilon and deltas, and there's a relationship there, that the choice of delta heavily depends on epsilon, right? So if you chose an epsilon such that the images are less than epsilon, the f of x minus f of a is less than epsilon, and you imply that x minus a is also less than delta. So can you imagine, when you say, for example, when you begin from here, you do not know, over here, you know it is f of a, but in general, when you evaluate this over here, this you would use a point in the random point in the domain, and you do not know the pre-image of that point, if that even exists, if there exists an a such that which is equals to that thing. So going the other way, sometimes it is a bit difficult, given that you do not know the function. If you know the function, you can study the reverse implication, but in general, you have to be very careful when you define things, and where you define things. I hope that answers what you were trying to ask. Great, perfect. The second definition, which is also a very famous definition, is that if f is continuous at a point A in R, if there exists a sequence such that the limit of xn goes to A, and that implies the limit of the images of that sequence at every point, meaning f of xn, it converges to f of A. If this implication holds, then f is continuous. And this holds for every a, or if you're talking about just one point, then it holds at that point, then f is continuous at that point. And notice that these definitions are so this is so different, but you can still believe me if I say the second one is roughly related to the limit definition in calculus. You can believe it, but that is still very different, because if you remember what a sequence is a countable collection of points. It is a list of points. But when you say limit x approaches to a, we are converging to it with a lot of with more, not just a countable collection, but a lot of, we can go as close as we want, uncountably speaking. So it is a bit different logically, but I will show it to you, that I will try to explain to you why these all three definitions, the one in calculus and these two, these two are equivalent. You can just simply, this is an exercise in real analysis, so if how the calculus one is related to these two. So before I go on about these, the geometric intuition for this, for the epsilon delta definition, you can see that when we say that the x minus a is less than delta, we mean that a delta neighborhood around a, meaning a plus delta, a minus delta. That's how neighborhoods or intervals are defined in real analysis. And that implies, f of x minus f of a is less than epsilon, meaning this is less than epsilon. And although this geometric intuition, I'm giving it to you on the identity function, which is not a very technical function, but this holds for any curve that you can think of. Think as difficult as you want, x to the power 5,000 plus something, and then it will still, this definition will still hold. And for each epsilon, there exists a delta. It just matters if you want to go into it and find exactly precisely what the delta for each epsilon is. Yeah, okay. Now, to see the equivalence, I would urge you to open a calculus book. And if you just remember, there might be, and I will give a reference for this. And if you open the book I'm using, which is Stewart's calculus, you will see that there is something called a precise definition of a limit, which is rarely used in calculus. And it is this one, that what does it mean? This statement that yes, Vajidbhai, we are first choosing an epsilon, and that choice of epsilon gives me a delta. And basically, I first fix an epsilon. I'm not choosing an epsilon. Basically, I'm given an epsilon. I choose a delta such that this or the continuous definition holds. And as I said, okay, there are a few examples missing, and I will try to add some precise examples after this meeting when I upload the slides on the website. You will find examples near these definitions, either just after it or before it, to motivate these definitions. So, and as I will try, I don't think I have any precise definition, except for one instance when I show you how to choose a delta. Just hold on for that, I guess. Okay, so as I was saying, if you open a calculus book, and this calculus book that I am using, there will be something called a precise definition of a limit, and this will be that definition where this expression, that limit x approaches to a of f of x is equals to L. What does this mean? It means that for every epsilon, there exists a delta such that this implication where x minus a less than delta greater than 0 implies f of x minus L less than epsilon. The reason why there is a greater than 0 as well over here, because when we are considering limits in general, we do not know that we do not allow x to be equal to a. Okay, and that is just a technicality that we use to differentiate the definition of a limit from the definition of continuity. But I think this explanation, this definition alone is enough to convince you from going from just this line over here, that limit x approaches to a f of x equals to L, and to get this first definition in real analysis. You can see that they are equivalent in some way. right? If you can't, I will maybe spend more time on why they are equivalent. If there are any questions. Okay, I will continue. So, as I said just right now, that using this definition, it is easy to see the equivalence between calculus definition of continuity and the first year analysis definition. But we never used epsilon or deltas in calculus, as I remarked before, because we always dealt with polynomials, exponentials, trigonometric functions. We never felt the need to use them, right? So that is why we in calculus we were not bothered with it. But when you get to real analysis, any teacher in real analysis might have told you, okay, this is a function, for example, f of x equals to x to the power 3, which is the cubic function. Show that it is continuous with respect to the epsilon delta definition. I think that is one of the examples that I will add later on. And it is worth going through that example to see how a choice of given any epsilon, if I give you epsilon, for example, 0.0.5, how that can be translated to get a delta, to find a delta such that in this implication, the implications of delta less than delta implies less than epsilon hold. Yeah, I will try to upload a example with a proof as well, that using the definitions. Okay, so now to now that we know what we are talking about, we have a definition in calculus, we have a definition in analysis, and I believe everyone now has a good idea of what continuity is, right? So let's start looking at some powerful results. Now, I know many people find this difficult sometimes, but we are going to first study linear algebra. Interestingly, continuous functions can be there. The continuity of the Thome function. Can you tell me what the Thome function is? THOMAE 2211165.
Hello, sir. A Tame function is actually it is continuous on every irrational point and discontinuous on all rational points. But uh, uh, I want to know the exact idea. I have some trouble in this. I
Uh-huh.
don't know the idea clearly.
Okay. Can you give me a more precise definition of what Thome function is? Let me see if I can share the whiteboard. Now, how
Sir,
do you
he says
define
the
it?
Tome function is a function which gives a zero on every irrational number.
Mm-hmm.
If we take a rational number in the form of p by q in the lowest form, it will give us 1 over q.
So,
Current function, yeah, Tome function, everyone.
so this is what you're saying, right? If zero on irrationals and one on rational.
No, sir, he says that x belongs to p by q, and the one, instead of 1, we write 1 over q.
Okay, okay, okay. So you write 1 over q over here, and instead of zero, you say you write p over q. Is that what you're saying?
So
No,
if x belongs to q, then we write q in the form of p by q, in the lowest form.
Okay, in the p by q. Okay, that's correct.
Sir, we says that from x belong to q, from q and the side of q, we write p by q. Instead of q, we write p by q.
Uh, I'm having trouble understanding where p by q comes.
Because every rational number can be written in the form of b by q
Yes,
in the
yes,
lowest form.
yes,
So
yes, yes.
if we take a rational number p by q, the
Mhm.
answer will be 1 over q.
Oh, okay. Thank you. Thank you. Yeah, that makes sense. Okay. Okay. Let me see if I understood correctly. You are telling me that a function goes from Q, let's just say to R, such that f of P by Q, which is the lowest form where P and Q are integers, it goes to 1 over Q. Is this the function?
yes, exactly.
Okay. And this is you're saying is continuous, right?
Not, it's not full function. The total function is defined from R to R, and the
Ah,
function from Q to R is same as you have written. and the function from irrational to R gives 0.
All right,
That is the
perfect.
full.
Okay, now I understand. Perfect, perfect. Yes, we can talk about this function. This is a very interesting function, by the way. Yes, it is. Okay. So f of x, let's say it is equals to 0 if x belongs to irrationals. That's what you said. And 1 over q if x equals to p over q belonging to rationals, right? Okay. So this function, and why is it continuous? So if you look at it carefully, can you, if you believe me, that can you see that 1 over q is very close to 0? First, can you believe this fact for me, that given a rational number, we can get close to q? For example, if I am given 2 over 100, okay, it is very close to 0, right? The distance from this to 0 is very small, 0.02. Does that intuition help you? Can you understand that? Okay, okay. Yeah, okay. If I mean, we can discuss it right now. I'm not going to take a lot of time on this. I just want to, for you to I'm not going to formally prove this, and you can easily prove this, but the idea of this function, it goes like this, that given any, if you're trying to prove continuity, okay, first you need to check where you're proving continuity. You're proving continuity on the whole of R. So we check that if f is continuous on the rationals, and we know that for every rational in the neighborhood of a rational, we can find so many rational numbers, right? But what we need is that they are close to each other. They are in a delta ball, right? So we can come up with a formula. Given any rational number, we can show that there are so many rational numbers close to it in the domain over here as well, and as well as in the function, which is it will be difficult to draw this function because there are rational and irrationals involved, but if you can believe me, it will be something like this: broken pieces of the rationals like this because of the 1 over q, and 0 otherwise. So you will always be able to see that these broken things are very close to each other. So you'll always be able to find a delta such that uh, choose a delta such that the implication holds. I will try to give a formal answer to this in the examples that I will upload. What if p and q equals to 1? Okay, and then we are, as Wajid Bhai is asking, with this point, right? F of x, where p and q are equals to 1. And interestingly, that is a fixed point, that meaning that f of 1 will be equals to 1, right? According to the definition of the function. So when we look again, when we look close to 1 on this, we look at an epsilon neighborhood over here. Going back over here, we can find a delta, right? Such that this function, it does not break in some sense, right? So what I'm trying to say, I mean, if you look at it carefully, yes, you see it going down to 0, then coming back up again. But in the sense of closeness, nothing is too far away, because there's a subtlety when you're talking about rational numbers. And I will try to add more comments to it when we get to the end of the session. I will try to speak more about it. And that is very technical, dealing with the rational numbers and continuity because of the density. So for now, let's just return to the talk. And if we have time in the end, I will be happy to answer this question. This is a very interesting question. Okay, so as I said, we just know the definitions of real analysis and calculus, and now let's see some very powerful results. Now, if you remember your linear algebra class, there you must have studied a definition of linear transformations, where a linear transformation is a function from Rn to Rm such that these two conditions hold, that the product, the image of the product is equals to the sum of the sorry, the image of the sum of two vectors is equals to the sum of the images, and the scalar multiple image of the scalar multiple of a vector is equals to the scalar multiple of the image. Now, I will tell you a very interesting thing, that all linear functions might seem basic to you if you're thinking only in terms of one dimension, but this fact that a linear transformation is continuous, it holds in higher dimensions as well. Just by these two properties holding, we can easily show this inequality between the norms of the images and of the domains vectors. And now you will ask, and at the end, just by looking at this inequality, you can say f is continuous. So, and you will ask me, how do I know that this inequality is enough to ensure continuity? I will tell you, okay, fix an epsilon greater than 0 and choose delta such that it is equals to epsilon over a. And now if you can just do some arithmetic in your head, suppose that delta is equals to this, then you can just connected is. So the first thing we have,
Excuse me, Asan, I have a question. If you could go to the previous slide.
yes, definitely.
In this slide, first we have to mention that in the theorem that the absolute value of x minus y is less than delta.
Yeah, yes, that is the how the implication goes. That, for example, this definition. First, you fixed an epsilon, then you claim that you chose delta, which is that choice, which was epsilon over a. And then to prove this implication holds true, what do you need to do? You need to suppose that this thing is less than this, x minus a is less than delta. You suppose this, and then so using this supposition and this inequality, right? This inequality, you just input this is you can add another inequality on the left over here and say that this f of x minus f of y is less than equals to a times epsilon over
Yes, I
a.
got it now.
Perfect.
Yes, but I just asked it because I didn't see in here that it is written
Yeah.
the absolute value of x minus y is less than delta.
Okay, very good. Thank you for asking.
That's
Maybe
all.
someone else was also wondering how this holds. Thank you. So, as I was saying, so connectedness. First, we need to understand what a connected set is. So a set X, and the best way to define a connected set is first defining what a disconnected set is. So a set X in Rn is called disconnected if there exists two open sets of Rn. I'm pretty sure you have some idea or notion of what open sets in Rn are. They are balls or union of balls, such that U intersection X and V intersection X are disjoint, and U intersection X union V intersection X cover the whole set X is equals to X. I will give an example to maybe visualize to show you what a connected set looks like. And a connected set is one that is not disconnected, right? And we can understand that even more simply by just reading, thinking about it. So the theorem goes that if X is connected, X is a subset of Rn, right? And f is a function that is continuous from Rn to Rm, a general continuous function. It can be linear, it can be anything, it can be any weird continuous function. Then f of x is also connected, meaning the image of x that sits in Rm is also a connected set. Now, this is very abstract. So a very simple example of maybe this happening is when you imagine the circle, which is traditionally denoted as S1. This is the subset of R2 with all vectors with norm 1 or distance 1 from the origin. And if you map F, any weird type of map, it basically distorts the whole circle, right? If you even consider that map, this is still a connected portion or connected part of R2, right? This is still connected. So given any F that is continuous, and maybe you can stretch it as much as you want, you can do anything with it, the geometric operations on Rn and R2, and you land in something which is an R2, which is not a circle, but it is still, at the very least, you can say it is still connected. I hope this example shows you how the continuous functions preserve connectedness. They can break up, they can stretch the set, they can distort it, but some properties remain preserved like this.
Awesome.
Yeah.
If circle mapped to a shape, it's okay. But if this circle mapped to a curve, like not a closed but a curve, but it is also connected, is it
Mhm.
possible to map a circle on a curve in that continuous map?
Okay. Short answer is no, it's not possible. Why? Because, okay, I will explain this in a picture. Wait, I can make a quick picture about this. Okay. Uh, Let me erase this for now. Okay, clear. Okay. What you're saying is that you're given a circle and you're saying that F is a continuous map that maps it maybe to something like this, where this is closed, right? Is that what you're saying?
Yes, sure.
Okay. So imagine doing this. If you also know a bit more about continuous functions, you know that if F is continuous, then the restriction is also continuous, right?
Yes.
So let me give you a new set, which is this blue one, which is a green one, sorry, which is a circle minus 1 point. And traditionally, because I'm doing this, I'm removing 1 point over here as well. And this is basically the restriction f to s1 minus, say, a point p, right? This function, green over here. Now, I will ask you this. Is this thing connected? Yes or no?
Yes.
But is this connected?
But there is a issue. If you remove a point from a circle, but when we uh, come to curve, so we are removing a point from the mid. So it might be possible this point is mapping on the boundary of the curve.
Yes, that is true. And I will answer this question when I discuss the next property, which is compactness. And for now, if you do it from the middle, connectedness will fail. But if you imagine, okay, and your question is valid, like if, for example, if I'm not removing the middle one, I'm removing the end one, right? Then this is open and this is everything is green. Then this set fails to be compact. And this, which is on the next slide, which is another property that is preserved by continuous functions.
Okay, okay. In next slide, I will ask this question
Okay.
again.
I will try to answer it over there as well. Okay. Okay. Let's see. So connectedness. I hope everyone agrees that okay, this is understandable to everyone. Okay, compactness. A set K in Rn in general, the n-dimensional real space, is compact if and only if it is closed and bounded. This is a very famous result from Heine-Borel that was given, that classifies all compact sets in Rn by just checking if they are closed and if they are bounded. So a theorem that says that if K is a compact set and f is a function, capital F is a function from Rn to Rm that is continuous, then the image of K, f of K in Rm is also compact, meaning it is also closed and bounded. And this is quite interesting because in general, the image of a closed set is not in general a closed set. And the image of a bounded set does not necessarily have to be a bounded set. But if you add both conditions together, if you have a closed and a bounded set, then the image is also closed and bounded, which is quite interesting just because of continuity this fact holds. And the first example that I want to give to you to make you understand this is that the 0, 1 interval, the closed interval 0, 1, which is famously compact because it is definitely closed because it's a closed interval, and it is bounded because it is uh, of length 1 in the real line. And a continuous map gamma from this to R2, imagine it just stretching it and maybe going through it again and going anywhere, but stretching it, but it still remains within these bounds because you cannot stretch them to infinity or stretch them anywhere continuously. Otherwise, the continuity condition will break. So this is an example of a continuous map. And if you know some topology, then you know this is the precise definition of a path in R2. And yes, so coming back to the example of a circle is also an example of a compact set. And if you, again, if you map it to a curve, a line segment or a curve segment in R2 and remove one endpoint, you can imagine in your head, if you have some intuition on topology or of closed sets, the complement of that curve with one open end will not be open, because in the complement that point will be closed, and that point will break the openness of the complement, and hence that set, that line segment or curve segment without one endpoint will not be closed, if you can imagine that. Okay, yeah. So the intermediate value theorem, okay, this is one of my favorite theorems. I really like this one because it is about a map f continuous from the closed interval, which is both connected and both compact. And these properties are very important when you're proving this in the setting of real analysis. So the function goes like this: if f a to b, from the closed interval a to b is to the real line is a continuous, and let's suppose f of a is less than f of b, it can be the other way around, it does not matter, then for any z which is in the image interval, and I claim that it has to be an interval because the image of a connected set has to be connected, and it has to be a closed interval because it has to be a closed and bounded set. So there exists a c belonging to the domain interval such that f of c is equals to z. In other words, every point between, to just motivate this, every point between this interval f of a and f of b is realized by at least one point in the domain. There is a solution for this. You might have also seen the intermediate value theorem used to find or to prove the existence of root theorem, which is a very famous theorem in calculus and analysis. And I hope these geometric pictures, these pictures below of graphs serves as some intuition onto why the intermediate value theorem is true. And I tell you, this is a very powerful and very fundamental theorem, which is used constantly in higher level mathematics to show even the most basic things like existence of a solution or connectedness or something of that sort. Yeah. And the last result that we will see, that is the powerful result, is the extreme value theorem, where it says that if f is a continuous function or from Rn to R. Now, if this is a function going from the n-dimensional space to the real line. Then, and if k is compact, then there exists an x minus and x plus in k such that f of x is equals, f minus is equals to the infimum of f of k, which again, if you see, it should be a closed and bounded set. So it's a bounded set, so the lower infimum f of k is and should be a finite number, and there exists a point in the domain such that f attains that finite number, which is the infimum, and the same for there's another point, or it might be the same point, that such that it is f of x plus is equals to the supremum of f of x, f of k. And in this theorem, we can also substitute infimum and supremum with min and max. This theorem basically tells us that we can do that easily, right? To motivate this, I have chosen a very simple function, which is f of x equal to sine x over the closed and bounded interval 0 to 2 pi. And if you know about the sine function, you know precisely what this x plus and x minus are. I have chosen a very simple example on purpose and chosen a compact domain to convince you that, oh, I'm so sorry, this should have been f of x plus and this should have been f of x minus, sorry. Because these are points. So, oh no, sorry, no, I'm sorry. There's nothing wrong, yeah. So the point being is that there are values on the x-axis such that these minimums and maximums are attained. And this is a again, very powerful theorem given to us just by using continuous functions and properties of the real of Rn. Okay, yeah. So that, as I said, that was my last result, and the references that I have used are this is Stewart, sorry, I will change this, Stewart, and calculus, and a very old book of analysis from Bartle, which is Elements of Real Analysis. Yeah. And